Okay, now here is my, I guess you can think of it as a dilemma.
Everyone just gets A's and we all pass. I answered your dilemma for you.
Notice I haven't said no yet. Okay. Well, that's. Okay, what did I miss?
Robert said the Dr. Dean method.
Oh, yeah. I mean, I tell students who are taking a class from Dr. Ding.
It's okay.
That the first test is a bloodbath, and then he gives you a chance to make up for it, so don't worry about it, and it's a ritual. Yeah.
Has to get the proper panic out of the students first.
Yeah, and it may not be the end result of an A, but at least it's not the F that everybody thinks they're getting at first. So.
He actually didn't do that ritual for his summer course. It was very strange.
Yeah, I made the course he got in the summer, I made a D on the first test, like a B on the second one. Somehow I made an A in the course.
Oh.
I just feel like these numbers don't add up.
All right. Well. Yeah, that's interesting. Well, apparently for some classes, like in the summer, he'll say like everyone just gets a B, or maybe at least a B. And then faculty meetings, he'll talk about how American students are weak. And okay. Anyhow, yeah, let's memorialize this on YouTube. Okay, my aside from my dilemma for semester as a whole, the dilemma just for today is okay. So I have my notes, ready to cover stuff. But when I look at what's up next to be covered, so of the 7 homework problems, I've covered enough for you all to do the first 5. And then the material in this chapter will go ahead from there for problem 6 and 7. But you all are on problems like 2 or 3, thereabouts, right? Or did anyone go further than that? Right. Okay.
I haven't completed any.
You have a what?
I haven't completed any.
Oh, okay. All right. Because the notes I have here for chapter 4, it's not very much. It's like 7 pages. But I also budgeted 2 full weeks to cover them. Oh wait, actually I'm not sure about that. Okay, so the 5th today, the 7th, then the 12th and the 14th. Yes, 2 full weeks. The week after that is fall break. Can't wait.
I start teaching next week on the 13th.
Okay, and then immediately get a break? Sure.
Yes.
Okay. It always work like that.
The 8-week students are going to be thrilled until they see what's all due right before when they come back, because they have a test the Monday after fall break.
So, in other words, there's no reason why I can't take this time to throw it open to more homework questions, and then, as time permits, can still go ahead and cover stuff. So, which at the moment I'm not really feeling that, but I can get myself in the mood if I need to. So, but yeah, I mean, time is very much on our side.
For once.
Yeah, so this is the vortex within your universe in which that is true and nowhere else. And I guess the same applies for me. So how is the homework going? Okay. Let's see what we can do about that.
So I was working on 2. I had 2 B's, the one we have to use do the 4th order.
Right.
What do the first and the last rows of the matrix need to be for the fourth order accurate case?
Okay, so so what happens in that case is since the boundary conditions are 0, okay. All right. So, because for all the other rows, the fourth order stencil that we're using, actually need to cheat for a moment here and recall what certain coefficients are supposed to be. All right, so this is for second derivative. Okay, so for all rows except the first and the last, using a centered finite difference, and it's fourth order. Now, to get fourth order accuracy for a second derivative, when it's centered, that would be a 5-point rule. So a 3-point rule gives you second order accuracy, the standard second difference. Add 2 more points, it bumps up to fourth order accuracy. So now I don't want to discuss the values of the coefficients right here, but that stencil, I'll label them this way. That these are the coefficients of like uj plus 1, uj plus 2, and then points to the left, uj minus 1, uj minus 2. So then your entries would populate these interior rows. And okay, so we have C0 on the diagonal. And for the second and second to last rows, one coefficient is left off, but that's okay because the solution is 0 on the boundary. So these finite difference rules for these 2 rows involve a boundary point. Now, the reason why we cannot use these rules for the first and last row is because now you'd have 2 values. We'd be relying on a point that's totally outside the domain, like past the boundary. And we don't know what that is. Also, unlike problem 3, we have no extra condition to eliminate using a point that's outside the domain. Because that's problem 3, you had a fourth order PDE, you have u 0 in the boundaries and ux being 0 in the boundaries, and that helped. But so what's needed here is to use a different rule. All right. So we use a unsymmetric fourth order finite difference scheme. And because it is unsymmetric, that's going to involve 6 coefficients. So how I can label those? Well, it'd be so for the first row, we would need C minus 1, C0, C1, C2, C3, and C4. So these coefficients are ones that will actually I need to label these are different coefficients. I'll put C tildes. So these 5 coefficients, all but the first, are ones that will actually go in the matrix. Now, if you're using my function that I posted, diff rule requires a vector of indices like for this one, you'd use -2 to 2. And the subscripts that I've used here are the indices for this rule, that you can pass the diff rule. And you're also specifying you want fourth-order derivative. That's how you can get the coefficients you need. So diff rule will return a vector of 6 coefficients. You're only going to use 5 of them in a matrix because this one's multiplied by a 0 boundary value. And down here, similar idea. You're going to have, I'll use hats to get to distinguish. Okay, and then C1 hat. So, so these will populate the last row. Okay. And since this second derivative implied all these coefficients are divided by h squared, but you're going to have that factor of h squared outside the matrix anyway. So, okay. So you need 3 finite different schemes altogether. Well, what you would find is you can get this rule just by replacing h by -h in this one. So actually the coefficients turn out to be just in reverse order. So does that answer?
Yes. And so for diff rule, would we just use like -1, 0, 1, etc. for the input of that? Or?
Yes.
Okay.
Yeah. Yeah, I chose the subscripting to conform to that. So that it understands you're dealing with, like, for -1 referring to u of x naught minus h, etc. So yeah, it is a rather strange matrix, unfortunately not. It would be symmetric. No, it definitely would not be. Silly me. That's okay. Okay. Well, first, are there any additional questions about, I guess, about this problem before talking about any other? Or does someone have questions about a different problem? Let me try now. I know we talked some about for problem 2, but it's possible to work out the exact solution for comparison. And then similar for number 3. Has anyone been able to work out the exact solution for number 3?
I have not looked at number 3 yet.
Okay. Well, good enough.
Just to take into consideration both.
Yeah, and then using the using the 4 boundary conditions to solve for the 4 constants of integration. Okay. Okay. All right, last chance for questions before I start covering stuff. Big Fred, I know.
Do you mind if I blow my nose real quick?
Oh, go ahead.
You mind greatly, Chelsea. We're getting all those monsters, the Irish blend ones delivered today. I accidentally ordered 2 4-packs on top of the 12-pack that I already ordered. So we're gonna have 20 of them. And that's including all the G-film that I have. Dr. Members, Robert keeps threatening an intervention against my G-fill consumption.
Okay.
Robert says it's a problem. I told him I just need a variety of flavors to keep myself happy.
All right, well. Okay. I'm trying something in Matlab first, so as far as what I'll cover. Okay. finding it. Okay. Okay. So what I've done to this point is about I find a difference for spectral methods in one space dimension. But so the very last problem is on a 2D problem. So how do you go from 1D to 2D? And basically, especially in Matlab, for finite difference, it's not very hard to do. So this chapter is largely about the numerical linear algebra aspects of solving these problems. But here, let's go through how we set up a problem in a 2D case. And then the rest of the chapter will be about, okay, you're setting up an AX equals B problem. What are some methods that can be used for solving it? And you'll recognize some of these things from 610. So now we have Poisson's equation in a rectangle. Okay. What we have is minus Laplacian of u is equal to f. And our domain, okay, so it's not just a rectangle, it's a square. So the interval -1 to 1 in x and y. And we'll assume that u equals 0 on the boundary. So whenever x or y is equal to -1 or 1. Okay. So, what we do is first come up with an AX equals B problem to discretize this PDE. We go back to 1D case. That would be what we've seen before. So minus uxx is equal to f. That's where that x or y -1 to 1, but really it's x. I need to fix that in the notes. All right. And then u equals 0 on the boundary there. Okay. All right. So now we know how to discretize this case. So for example, it could be the familiar center difference. So 2's down a diagonal, -1's above and below. Or it could be the differentiation matrix using Chebyshev polynomials, something like that. But the point is, we assume we have some matrix that handles one-dimensional differentiation twice with respect to x, so we'll have a 1D Laplacian. So then, to solve a 2D problem, once you have this matrix, in whatever form it is, set up a Ax equals B problem where your matrix A, I'll call it K2D to contrast with K1D. And here's how you get it. It's actually pretty quick. You take your one-dimensional matrix and take the Kronecker product, that's what this funny time symbol is, with identity, and then do it again in reverse order, and you add the two together. So one of these is for UXX, and the other is for UYY. And this is really easy to do in Matlab. As a built-in function for doing Kronecker products, it's called Kron. So you can make an identity matrix or a sparse identity matrix, make a matrix K1D in the ways we've described earlier, and just use Kron with those two. And that will be a discretization of the 2D Laplacian. All right. No. Oh. So actually, this is, well, let's see. Let's see. As far as, let's see. Thing to be careful about is, when I say one of these is for UXX and the other is for UYY, which is which depends on how you decide to order the grid points. And I'll get to that in a moment. But first I need to explain, what does Kronecker product actually do? So for general matrices, A Kronecker product with B, and it is not commutative. So like regular matrix multiplication, Kronecker product is also not commutative. The easiest way to describe it is you can think of it as creating a new, much larger matrix that is a tiling of B. And we'll assume that A is M by N, and we'll assume that B is P by Q. And the new product is much larger. It is the number of rows will be M times P, so the product of rows, number of rows in A and B. And in the columns, you also multiply those dimensions together, N and Q. So you can think of it as making a tiling of B, where each tile is multiplied by a single entry of A. So the first tile, if you will, is A11B. And then we have A12B, and then A1NB, and then so on, AMN. So you have M by N tiles, but each tile is the size of B, P by Q. That's how we get the size MP by NQ. Okay. Questions so far? Now, it's not at all obvious that performing this operation is the appropriate generalization of a 1D Laplacian to a 2D Laplacian. We're taking partial derivatives with respect to x and y and adding together. So what I can do is show you in this case what the Kronecker product will look like, and then I'll be able to show you from there. these terms one at a time. So 1D Laplacian Kronecker of identity, and then other way around. All right. Okay. So 1D Laplacian Kronecker with identity. What does that look like? Well, so you're tiling with identity, and within each tile, you're multiplying by the appropriate entry of K1D. So what that would mean is, down the diagonal, you'd have 2 times identity, and then you'd have minus identity in these subdiagonal and superdiagonal blocks. Okay. So each block is a diagonal matrix. It's a multiple of identity. So what this means is, when you multiply this matrix by a vector of u values, so you're taking a function u that's a function of x and y, but you have to represent that function of 2 variables by a vector. Now, it makes sense if a function of 2 variables to represent it by a matrix, because you have points x and y, points arranged on the grid. But for here, we have to reshape that into a vector. We have to decide how we want the points to be ordered. So I'm going to let uij be my approximation of u of xi, yj, just for shorthand. So here's how I'm going to order the points within this vector. So I'm going to start by, I'm going to be varying the y values. So I have u11, u12, u13 down to u1n. So let's suppose I have n grid points per dimension. So I've cycled through all the y values, but we have only the first x value. And then u21, u22, and so forth. I keep going all the way down to unn at the bottom. Now, if we consider in each of these rows what are the non-zero entries, well, here we have everything is 0 here except on the diagonal. Here again, everything 0 except on the diagonal. So non-zero entries here are spaced and apart. So here we're approximating second derivative using points that are listed and apart. Well, those are neighboring values in x. So like here we have u11 and its neighbor in the x direction, u21. These are spaced, these points are n apart in the vector. So because neighboring x values are n apart, then what I can say is this ordering, K1D, Kronecker product with identity, is a discretization of the second partial derivative with respect to x. I have to put a minus in here because we started with Poisson's equation in one dimension that had minus uxx. So because I ordered the points this way, this is second partial derivative with respect to x. Whereas if I had ordered the points differently, like u1, 1, 2, 1, 3, 1, so everything opposite, like the, so basically the transpose, then it would be second partial minus second partial derivative with respect to y, is what this matrix would represent. So how you order the points on the grid when you represent your solution as a vector is very important. Now, for this problem, you have minus uxx minus uyy. So you can use either ordering and you're still going to get to 2D Laplacian. But for other PDEs, you have to be very careful about making sure the ordering that you use works with the PDE that you have. So by contrast, if I go the other way, identity, collaborative product K1D. So now we have a tiling of 1D Laplacian, where each tile is multiplied by entry of identity, but all of those will be 0, except on the diagonal. So I'm just going to have K1D all the way down the diagonal, and nothing else. So what's happening is this is acting just like the 1D Laplacian on points that literally are next to each other in the vector. Well, neighboring points within the vector are neighbors in y. So this is for discretization of minus second partial with respect to y. Again, with the ordering that I've chosen. The questions about what the 2D differentiation operators look like. Now, here's how you can arrange all this in Matlab using its functions. Okay. So you choose the number of grid points per dimension, n. So then I'll let h be the spacing. So in this case, we're on the interval -1 to 1. So h would be 2 over n plus 1, because the interval we're on, -1 to 1, is of length 2. So it's the size of the interval. So then you can define x would be your endpoint -1 plus h times 1 to n. I don't really have to make it a column vector. I just like column vectors. They're nicer when you display them at the prompt. So now I have my grid for a one-dimensional problem on the interval -1 to 1. But now what I want is a grid of points. Now I want to look at the square, -1 to 1 in both directions. How do I get those grid points? So So what you do is use Matlab's mesh grid command. Okay. So you feed it a vector of x values and a vector of y values. In this case, they'll be the same because we're dealing with a square. What it returns are matrices, n by n matrices of x coordinates and y coordinates. Okay. So now you have the x and y coordinates of your grid points. And then, but the thing is, now you want the points, you want vectors of your x values. So what you can do is, I can reshape. So if I want to make these into a column vector, So those empty square brackets means just take however many entries there are, and so you specify it as one column. So now you have a column vector of all the x values, and a column vector of all the y values. And yes, I learned about this from Chelsea, thank you. Okay, and so y2, same thing. All right. So, and what that will give you, based on how reshape works, reshape takes a matrix and makes it into a column vector by going through a matrix column by column. So it'll put the first column, then the second column below that, third column below that, and so forth. Now, because I ordered my outputs in this manner, x2 first, then y2, I get this ordering. If I swapped, if I have y2, x2, then it'll order points in the opposite manner. And that's just based on the conventions of how Matlab reshape, how Mesh Grid formats its output, and also how Matlab reshapes matrices and vectors using what's called column major order. Or some programming languages use row major order. Fortran, on which Matlab is built, is column major order. C, C++ uses row major. Okay. So then if I have a function f for my PDE, I can evaluate it at all of these grid points, and I have my right-hand side vector for my AX equals B problem. And I've shown you how to form a matrix. You know how to form a one-dimensional version, and you use cron to get a two-dimensional version. So now it gives you what machinery you need to set up a two-dimensional Poisson's equation, finite difference solver. If you wanted to use a spectral differentiation matrix, like a Chebyshev differentiation matrix, you could do a lot of the same things. The key difference is here you would not use equally spaced points. You would use the Chebyshev points, a -1 to 1, just so your function f is evaluated at the correct points. But otherwise, all the rest of this would be the same. Okay. Questions about any of this? Okay. When I started finite difference, I had shown how to get finite difference stencils using Taylor expansions. You can do that in higher dimensions. You're just doing a multivariable Taylor expansion. So that would be a way to get the entries of these matrices directly instead of building them up from one-dimensional matrices using cron. But that'd be pretty tedious. Okay. All right. Okay. Real quick, 3D is a direct generalization. So your 3D Laplacian can be built up from a 1D Laplacian by doing a threefold Kronecker product. This would be like for UXX again. And then order differently for UYY. And then one more ordering for UZZ. It's all the same idea. All right. You know what? I'm going to be lazy. Well, no, I can't. I was thinking like I could use a whole over half of the board and just move the computer, but I got to take a picture of this stuff anyway. Okay. So, refresh your memory, the 1P stencil for Laplacian uses 3 points. So Laplacian, approximate Laplacian at xi using points I plus 1 and I minus 1, and they have the appropriate coefficients. So we have minus 2, 1, and 1. Now, what about two dimensions? Now, what I just showed you is that you use this stencil for uxx, and then again for uyy. So you have a total of 5 points that are arranged this way. I have ij, I plus 1j for the x direction, I minus 1j, and then I have ij plus 1 for the y direction, ij minus 1. And the coefficients will be minus 4 for a point in the middle, because you have 2 of these, one for uxx, one for uyy. They get added together to go here, and then 1 is everywhere else. So that's a 5 points stencil. Okay. Now, there is another stencil that's commonly used for these situations for Laplacian, and that is the 9-point stencil, which I actually do not have here the notes, although I believe I have it in the book. Hopefully I have it there. I remember putting it in. I thought I did anyway. Maybe I didn't. Oh, interesting. Okay. Ah, I do have it. Okay. 9-point stencil. So to reduce clutter, I'm just going to write the coefficients. So the indexing works exactly the same as you just seen, but now we have just more points involved. So the coefficients are, so in the point in the middle, you have minus 20, and then at the corners, the coefficients are 1. And then at the other points, coefficients are equal to 4. And what you see is if you added up all the coefficients, you get 0, which makes sense because the Laplacian of a constant function has to be 0. Okay. Now you might think, why use a 9-point stencil? Your matrix has more non-zero entries. So you're losing efficiency. And yes, that's true, but Gaussian elimination for a matrix of more entries would incur cost. But there is a distinct advantage to using the 9-point stencil. So the local truncation error, LTE, that if you use the 5-point stencil, and I'll just use a subscript 5 to indicate 5-point, that is equal to the exact Laplacian. And here's the error term, so second order accurate. And what you get is these higher order derivatives. U xxx plus u y, and then the rest is order h to the 4. So this is the leading error term. Okay, which makes sense because for one-dimensional case, the error in the Laplacian is involves h squared over 12 times the fourth derivative. So now we just have the sum of those for x and for y. What about the 9-point? That's equal to the exact Laplacian. And then the error in this case, again, we have h squared over 12. And then we have same terms, except with one additional one, 2uxxyy plus uyy plus order h to the 4th. Okay. Now, I think, okay, big deal. In fact, it's even worse. We have another term here, except for one thing. This is actually what you get if you take the Laplacian of u twice. Okay. Now, the reason why this is a big deal is if we're solving Poisson's equation, minus Laplacian of u is equal to f, we know what this is. In other words, we literally know what the error term is, the leading term. So we can incorporate that into our right-hand side of our ax equals b system, and therefore get rid of this error term, and then the error will be order h to the 4th. This is what you're doing in the homework, problem 2, part.
I think that's part A.
C.
C?
Yes. Yeah, so it's a one-dimensional version of it, but it's still the same idea applies. Because anytime you can know your leading error term, that's huge. So definitely jump all over that and get rid of it. So because of the form of the error in the 9-point stencil case, can't do the same thing because you can't express this in terms of something you know. So that's why some people like using the 9-point stencil. Okay. So this idea here is called deferred correction. Which is actually used not just for Poisson's equation, but any situation where you're able to figure out a portion of your error and eliminate it from your approximation. That term is associated with it. And I will never forget, very early in my career, when I was at a conference, and the speaker was giving a talk about deferred correction, and he said, he opened by saying, well, this talk is about deferred correction, so if I make any mistakes, I'll fix them later. So, yeah, and so he got his groan and moved on. Okay. All right, so So what I've discussed here is for solving Poisson's equation in 2D, here are certain ways that you can set up, or even in 3D, here is how you can go about setting up a system of equations AX equals B, or I guess AU equals F, where A is K2D or K3D, whatever discretization of Laplacian you want to use. Whether that, and I'm focused on finite difference, but it can also work for spectral, where you choose the appropriate one based on your boundary conditions. Like if you're solving Poisson's equation in a square using periodic boundary conditions, then that would lead to the one differentiation matrix I showed you involving cotangent. Whereas if it's not periodic, then you can use a Chebyshev matrix. So if you're solving Poisson's equation, then you have some AX equals B problem, or A equals F problem that's going to fall out of this. Then the question becomes, once you have that, how do you solve it? What are the best? What's the best approach? You are familiar with certain methods from 610. There are direct methods, Gaussian elimination, Cholesky factorization, which can help with Poisson's equation, because the negative Laplacian is a positive definite operator. Ideally, it should be discretized by a symmetric positive definite matrix, so you can use Cholesky. There are also iterative methods. In 610, you learned about what are called non-stationary iterative methods, Krylov subspace methods like conjugate gradient. There are also stationary iterative methods. I did not cover those in 610. I will cover them in 561. Well, actually, all of you have taken that class except Chelsea. So. That's okay, not missing much.
Read the textbook, you'll figure it out.
Oh yeah, it's all in there. Jacobi, Gauss-Seidel, that sort of thing. And I will spend some time talking about these things in this class. So as a result of those, and then there's multi-grid methods that are built on the stationary case. I will spend some time on that. That's the subject of problem 6. And the multi-grid methods is a very active area of research because it leads to very fast methods for problems like these. If you have a different sort of PDE, because at the beginning of the class I talked about Laplace's and Poisson's equation, but I also talked about heat equation, wave equation. So when you discretize those in space, you do not get AX equals B problem. You get a system of ODEs. And time-stepping methods are used to solve for that. So after I finish with this chapter, I will cover that stuff. So in fact, actually, yeah, you'll get everything that you would have gotten in 561. It'll just be taught right here. So you're not missing anything. Okay, so that's just how things are laid out for, is that the remainder of the semester? Yeah, pretty much. So at least I can take my time doing it. Okay, so yeah, so all those classes and methods I was just listing off, I will get into those as I continue this chapter. Now, okay, we are almost out of time. And the thing is, what I plan to cover, what I needed to cover this week is exactly what I already did today. So, okay. And I realized that, when I ask you all, here in this room, if y'all have any questions, and I can hear a pin drop, or whatever's softer than a pin dropping, I can hear that, probably.
My nose ring getting flung out my face when I scratched it.
What?
I really did. I was scratching my nose and my nose ring flung out. Didn't even hear it drop, so it's gone.
Oh, ouch.
Oh, it didn't hurt.
Oh, okay. Well, that's relief. Sound like it might.
Looks like an L shape, so it has the L like hooks in there and holds it in the face.
Ah, okay.
So you just lift it out like that to pull it out, and I guess when I scratched, I did that.
Oh,
I still
okay.
don't know where it went. It's gone.
Okay, so at least it was like a removed the way it's supposed to be.
Yes.
Okay.
But not intentionally.
Yes, yeah.
So now I
Okay.
get to go home and find another one that I like to wear.
Ah, okay. Oh, good enough.
Yes. I
Um,
was surprised as I'm kidding because I probably could hear a pin dropping.
oh, yeah. So what I'd like to try on Thursday is doing something a little different. Since there's definitely no need to continue through the notes, so I won't like formally hold class, but I'll basically just make it an office hour where I'm literally in my office. So if you have questions and you don't feel like asking them out loud, then you can stop by there. And Caitlin, since you're attending virtually, what you can do is you can if you can have questions, you can let me know. And because also since you're in my next two classes, so that also creates time to make sure that any questions you have are also addressed. So, but it'd be good if you let me know beforehand if you have anything, so I can make sure that you're accommodated. So I figure we'll be doing this from time to time because each week, I got to cover something, but it's not a ton. But I want to make sure that as we get towards the material for the final homework problems, that everybody is moving things along. So, okay. So I might see you on Thursday. We'll see. All right, stopping recording now.